To determine the appropriate size for overload protection for a 1 horsepower, 1.7 amp motor, several key resources and guidelines should be consulted. Firstly, the National Electrical Code, specifically NEC 430.52, provides essential regulations for motor protection. Secondly, IEEE 241-2022, which is the IEEE standard for electric power systems in commercial buildings, offers further guidance on electrical systems, including motor protection. Thirdly, it is crucial to refer to the motor manufacturer's recommendations, as they often provide specific overload sizing recommendations in their product literature or technical support documentation. In general, an overload protective device should be sized to trip between 115% and 150% of the motor's full load current. For a 1 horsepower, 1.7 amp motor, a common overload setting of 125% can be used to calculate the trip current. Trip current is calculated by multiplying the motor current by the overload setting. In this case, the trip current equals 1.7 amps multiplied by 1.25, resulting in a trip current of 2.125 amps. When selecting an overload protective device for the starter, it is recommended to choose one with a trip current setting slightly above 2.125 amps. For example, a 2.25 amp or 2.5 amp overload protective device could be suitable. It's also essential to consider the motor's operating conditions, such as anticipated load variations or starting torque requirements, as these factors can influence the optimal overload size. A thermal overload relay should be used for continuous protection against overloads, as it provides reliable and consistent performance. The overload relay must be installed in the correct location within the starter circuit to ensure it functions properly. Regularly inspect and test the overload protective device to verify its functionality and ensure it trips as expected. This helps maintain the motor's protection and prevents potential damage from overloads. To elaborate further on the National Electrical Code, NEC Article 430 covers motors, motor circuits, and controllers. Section 430.52 specifically addresses motor overload protection. It provides detailed requirements for selecting and sizing overload devices to protect motors against excessive current. The code emphasizes the importance of selecting overload devices that will trip at a current level that protects the motor winding insulation from damage caused by prolonged overcurrent. The selection process involves considering the motor's full load current, service factor, and temperature rise. The NEC provides tables and guidelines for determining the appropriate overload protection for various motor types and applications. Regarding IEEE 241-2022, this standard offers comprehensive guidance on designing and maintaining electrical power systems in commercial buildings. It covers various aspects of motor protection, including overload protection, short-circuit protection, and ground fault protection. The standard emphasizes the importance of coordinating protective devices to ensure selective tripping and minimize downtime. It also provides recommendations for selecting and applying overload relays, fuses, and circuit breakers for motor protection. Motor manufacturers' recommendations are invaluable because they are tailored to the specific characteristics of their motors. These recommendations consider the motor's thermal limits, insulation class, and operating conditions. Manufacturers often provide overload curves that show the motor's thermal capacity and the corresponding trip times for different overload levels. These curves can be used to select the appropriate overload device to protect the motor without causing nuisance tripping. Furthermore, manufacturers may offer specific guidance on selecting overload devices for motors used in particular applications, such as variable speed drives or hazardous locations. When sizing an overload protective device, it is essential to understand the concept of full load current. The full load current is the current a motor draws when operating at its rated horsepower and voltage. This information is typically found on the motor's nameplate. The overload protective device should be sized to allow the motor to operate at its full load current without tripping, but it should also trip quickly enough to protect the motor from damage caused by overloads. As mentioned earlier, a general guideline is to size the overload device to trip between 115% and 150% of the motor's full load current. The specific percentage will depend on the motor's service factor and temperature rise. Motors with a higher service factor can tolerate higher overload levels for short periods, while motors with a low service factor require more sensitive overload protection. When calculating the trip current, it is important to use the motor's nameplate full load current, not the actual current drawn by the motor. The actual current may be lower than the nameplate current if the motor is not fully loaded. Using the nameplate current ensures that the overload device will trip even if the motor is lightly loaded. In the example provided, a 1 horsepower, 1.7 amp motor is used. To calculate the trip current using a 125% overload setting, the motor current of 1.7 amps is multiplied by 1.25, resulting in a trip current of 2.125 amps. This means that the overload device should trip when the motor current exceeds 2.125 amps for a certain period. When selecting an overload protective device, it is important to choose one with a trip current setting slightly above the calculated trip current. This allows the motor to handle brief overloads without tripping the overload device. However, the trip current setting should not be too high, as this could delay the tripping and allow the motor to overheat. In the example, an overload device with a trip current setting of 2.25 amps or 2.5 amps would be suitable. It is also crucial to consider the motor's operating conditions when sizing the overload protective device. If the motor is subjected to frequent overloads or high starting torque requirements, a larger overload device may be necessary. Conversely, if the motor operates under relatively constant load conditions, a smaller overload device may be sufficient. A thermal overload relay is a commonly used type of overload protective device. Thermal overload relays use a bimetallic strip or a melting alloy to sense a motor current. When the current exceeds the trip current setting, the bimetallic strip bends or the melting alloy melts, causing the relay to trip and disconnect the motor from the power supply. Thermal overload relays are available in various sizes and trip classes to match different motor characteristics and operating conditions. Trip class refers to the time it takes for the overload relay to trip at a specific overload level. Common trip classes include Class 10, Class 20, and Class 30. Class 10 relays trip faster than Class 20 relays, and Class 20 relays trip faster than Class 30 relays. The appropriate trip class depends on the motor's thermal characteristics and the application requirements. The overload relay must be installed in the correct location within the starter circuit to ensure it functions properly. Typically, the overload relay is installed in series with the motor windings and the starter contact. This allows the overload relay to sense the motor current and trip the starter if an overload occurs. It is essential to follow the manufacturer's instructions when installing the overload relay to ensure it is properly connected and calibrated. Regular inspection and testing of the overload protective device are crucial for maintaining its functionality. Overload relays can become damaged or drift out of calibration over time, which could affect their tripping performance. Regular inspection should include visually inspecting the overload relay for any signs of damage, such as cracks or corrosion. Testing should involve using a test kit to simulate an overload condition and verify that the overload relay trips at the correct current level. If the overload relay fails to trip or trips at the wrong current level, it should be replaced immediately. In addition to overload protection, motors also require short-circuit protection. Short-circuit protection is designed to protect the motor from high fault currents that can occur during a short circuit. Short-circuit protection is typically provided by fuses or circuit breakers. The fuses or circuit breakers should be sized to interrupt the fault current quickly enough to prevent damage to the motor windings and other components in the circuit. Ground fault protection is another important aspect of motor protection. Ground fault protection is designed to protect personnel from electric shock hazards that can occur if a motor winding insulation fails and creates a path to ground. Ground fault protection is typically provided by ground fault circuit interrupters, or GFCIs. GFCIs are designed to detect small ground currents and trip the circuit quickly enough to prevent electric shock. To summarize, sizing overload protection for a 1 horsepower, 1.7 amp motor involves consulting several key sources, including the National Electrical Code, IEEE standards, and motor manufacturers' recommendations. The overload device should be sized to trip between 115% and 150% of the motor's full load current. A thermal overload relay should be used for continuous protection against overloads, and it must be installed in the correct location within the starter circuit. Regular inspection and testing of the overload protective device are crucial for maintaining its functionality. In addition to overload protection, motors also require short circuit protection and ground fault protection to ensure complete protection against electrical hazards. It is also important to note that local electrical codes and regulations may have specific requirements for motor protection. It is essential to consult with a qualified electrician or electrical engineer to ensure that the motor protection system complies with all applicable codes and regulations. Furthermore, proper documentation of the motor protection system is essential for maintenance and troubleshooting purposes. The documentation should include the motor's nameplate data, the overload device's trip current setting, the fuse or circuit breaker size, and the GFCI trip current setting. This information will be helpful for identifying and resolving any problems with the motor protection system. Selecting the right motor starter is another key step. Motor starters are electromechanical devices used to control electric motors. They provide a safe and reliable way to start and stop motors, as well as protect them from overloads and short circuits. Motor starters typically consist of a contactor, an overload relay, and a disconnect switch. The contactor is an electrically operated switch that connects and disconnects the motor from the power supply. The overload relay protects the motor from overloads by tripping the contactor if the motor current exceeds a certain level. The disconnect switch provides a means of safely disconnecting the motor from the power supply for maintenance or repair. When selecting a motor starter, it is important to consider the motor's voltage, horsepower, and full load current. The starter must be rated to handle the motor's voltage and current requirements. It is also important to select a starter with the appropriate overload protection for the motor. Motor starters are available in various types, including manual starters, magnetic starters, and solid-state starters. Manual starters are simple, manually operated switches that are typically used for small motors. Magnetic starters use an electromagnet to operate the contactor, providing remote control and automatic overload protection. Solid-state starters use electronic components to control the motor's voltage and current, providing smooth starting and reduced stress on the motor and power system. The size of the wires connecting the motor to the starter and the power supply must also be properly sized to handle the motor's current requirements. The National Electrical Code provides tables and guidelines for determining the appropriate wire size for various motor sizes and applications. Using undersized wires can cause voltage drop, overheating, and even fire hazards. Proper grounding of the motor and the electrical system is also essential for safety. Grounding provides a low resistance path for fault currents to flow back to the source, tripping the circuit breaker or blowing the fuse and preventing electric shock hazards. The National Electrical Code provides detailed requirements for grounding electrical systems, including motors. These requirements must be followed to ensure the safety of personnel and equipment. In summary, ensuring the correct overload size for a motor involves a comprehensive approach. Firstly, refer to the NEC and IEEE standards. Secondly, understand the motor manufacturer's data. Thirdly, calculate the trip current and choose the correct thermal overload relay. Fourthly, install everything correctly and test it. Fifthly, ensure there is proper short circuit and ground fault protection. And finally, there should be regular inspections and documentation. By following these steps, it is possible to properly protect a 1 horsepower, 1.7 amp motor from overloads and ensure its safe and reliable operation.